Going to talk about today is all in this Google Colab. For people who haven't seen these, this is like a sort of a virtual machine that you can run somebody else's code on. So if you want to follow along, you can go ahead and execute code in tandem with me if you just go to this URL. And you should see something, you should see something that looks exactly like this. And then, so this is sort of the sandbox environment we'll be messing around with today. It's been a while since we did one of these, so just to recap really quick. So far we've talked about sort of the general introduction to machine learning and sort of what tools are available. So this is like the practical guide to how to find a data set, do the necessary pre-processing, load it up into the nice standard libraries we have, and start running some basic ML models. So we've done things like linear, logistic regressions. And so I'm not going to spend too much time today on the nitty-gritty of exactly how all that goes down. I'm going to go through it pretty quickly, but I think there should be videos of doing this before. So that being said, if people have questions or confused about anything as I'm going, or if it feels like I'm going too fast or omitting some key details, please go ahead and stop me and ask some questions. I guarantee you that if somebody has a question, somebody else has the same question. So what we're going to be focusing on today is after you've found a data set, loaded it up, run a little bit of modeling, what exactly do the numbers or the outputs on the other side of the machine mean, and how can you start sort of plotting things, and how should you pick your evaluation, and what do different evaluations mean. So to get started, we're going to import all of the standard libraries that we've been using so far along. Things like pandas is going to be our primary method of dealing with data. And then we're going to use things like NumPy and sklearn and SciPy to do all of our numerical processing and use their built-in machine learning models. And then we're going to be using matplotlib and seaborn as our plotting libraries. Again, this is all very, very standard off-the-shelf libraries that everybody likes to use. So if you get the basics of these down, you can do almost anything you need to do. All right, so the data set we're working with today is the same as last time, and that's going to be the IMDb reviews for 5,000 different movies. And so this is our big whole mess of pre-processing code. I'm going to go through this pretty quickly. I'm just going to describe what everything does and why it's important to do, but I'm not going to necessarily focus exactly on the syntax. If you run this in your local environment, you should be able to produce the same results. And if you want to sort of tweak stuff and see what happens if you change different things, please go ahead and do so. Okay, so the data set has a bunch of different columns in it. Let's go ahead and look down here at the bottom. So just to look ahead a little bit, this is what our data looks like. So here each row corresponds to one of our data objects, which in this case is a movie, and all of the different columns are the data we have for this. So here in the movies we have things like titles, their cast, their crew, their budget, genre, things like language. We have their production companies and all sorts of stuff. In this example, so there are lots of different tasks you might perform on a data set like this. Today we're going to be examining the task about predicting whether or not a movie is going to be profitable. So we're going to try and predict, learn how to identify movies where the revenue exceeds the budget. So there are three different types of data. If this sounds familiar to people, we've got numerical data. This is anything that sort of takes on a scalar value. So things like the budget is numerical value. Then we have categorical data, which is the data takes on sort of discrete values from different categories. So here, this is going to be things like the keywords or so here the keywords. There's some list of keywords that people use to describe movies, and each of these different movies is going to take on some subset of those keywords. And then finally, there's going to be ordinal data. I don't think there are any good examples in this data set, but this is data where The values are discrete, but they have some sense of ordering. So this is small, medium, large as an example of an ordinal column, where you can't necessarily average small and medium and get small into half, but you still have some sense of ordering within the data. So in order to process this, the key things that we're going to do are drop data that's incomplete. So we're going to do a little bit of a cleaning of our data set to identify things that don't have enough useful information. And then we're going to go ahead and convert some of the columns that are hard to work with into things that we actually know how to deal with. So we're going to drop all of the rows that don't have any value for the budget or the revenue. We're going to go ahead and convert these big gross looking JSON strings into like their component pieces. And then finally, the most important thing that we're going to do is convert into sort of these dummy labels, they're called. So if we recall from previous times, or just for general machine learning wisdom, in order to actually put a data object into a model, all these models are functions from one point in high dimensional space to whatever we're trying to learn. So this means that every column in our model needs to be a column of numbers that somehow represent what we're trying to learn. So for something like a numerical feature, popularity or revenue or things like that, we can just go ahead and write this number down. That's a number that has meaning. But for something like which language is used in the movie, or for something like which keywords occur for this movie, we need a way to represent that numerically. And so what we've decided, what the standard thing to do here is you just create a new column for each of these things that you're trying to represent. And that column is just going to be a binary label of, does this particular movie exhibit this characteristic, yes or no? So for example, this first movie, we've got a different column for each of the different genres that a movie might occupy. And we see that this first movie occupies the comedy and drama genres, but not any of the others. So romance, it looks like. So that's just what we're going to do to all of our data. We're going to take all of the data, extract all the columns, and then do a little bit of pre-processing on the numerical features. We're going to do things like scale them down to a standard mean, and then rescale them to unit variance. So this is just sort of normal pre-processing stuff. And then once we've scaled everything down and learned to extract the columns, one key thing that we're going to keep in mind when we're doing this is that we're going to, before we do any sort of decision making or any sort of looking at our data, we're going to split it into a train and dev and test set. So what we're going to use these different sets for is the train is going to be used for actually like fitting the parameters of whatever model we choose. The dev set is what we're going to do to evaluate our different intermediate models. So when we're experimenting with different things, we're maybe trying different models, we're tuning hyperparameters, we're trying to choose how to engineer features. Every time we try something new there, we're going to train our model on our training set, evaluate it on the development set, and use the output there, the scores there, to sort of make decisions. And then once we're completely settled on the way we want things, at the very end, we're going to have our final model, and we're going to run it on the test set, and that's going to be our final performance. And the importance of saving this test set to the very end is that if you make decisions about your modeling or your pre-processing or things like this based on sort of the distribution of the test set, then you're implicitly kind of guiding your model towards solving that specific test set, which if you spend a lot of time doing, you can get really, really good at solving any particular set, in this case your test set, but any sort of specific assumptions you make about what's going to work best might be specific to just that test set. And what we really want is to train models that generalize to stuff we haven't seen before. So we're going to take our data set, split it into train, dev, and test, and then generate these columns. So let's do that and take a look at what we get. So here we're going to look at the first row in our test set, and it looks like we've just got a bunch of different columns. There's columns for genres, about which genres it has. There's columns about the keywords. And then finally, there's some numerical columns here at the budget and the runtime. And these are going to be the inputs we use to try and predict this profitable column. And here in our pre-processing, we've defined profitable to be if the revenue is greater than the budget. So that's our setup here. This is a binary classification task. We have a bunch of inputs, a bunch of categorical data, and then some numerical data. So in our binary classification task, the simplest model that people run into a lot here is logistic regression. And so logistic regression is one of these kind of off-the-shelf linear land models. And what it's going to do is look at all of our individual features, all of our columns here, try and learn some weights on them, and then take a combination over those features and give us a probability about whether or not our selected feature is going to be profitable or not profitable. So this is provided by sklearn's linear model library, has tons of stuff. But the standard procedure here is we're going to instantiate a model, fit the model to our training data, and then predict. And here, again, we're going to use the dev set. So because we haven't made any final decisions about what we want things to be, we're still tweaking our model, maybe going to change things. So we're going to do it all in the dev. And then we can check to see how we did. So we can look at our predicted. We can even print the first 10 dev examples and print the first 10 actual labels to give us a sense of sort of how we do. And it looks, oh, okay, well this is, maybe this set isn't particularly informative, but we see the predicted labels are mostly true with one false here. And the actual labels are, again, mostly true, but a false in the second position and a false in the last position, which we didn't get right. So again, these labels are true if the movie made more money than they budgeted, and false if they made less money than they budgeted. So here, our overall accuracy ended up being 73%. And so this is a start to finish, pretty easy way to just take the movie data set and try and check to see if you just look at the budget, if you look at the runtime, if you look at all of the genres and keywords, can you sort of estimate how whether or not a movie is going to be profitable? And it says 73% of the time, yeah, no problem, you get it right. Which brings us to our sort of first big topic of the day, which is how do we actually evaluate a model? So we got a number, we got 73%. We picked a metric, we picked accuracy, which is a very easy, intuitive thing to measure. And now we have to figure out, what does this number mean? So the absolute value of our metric, so here we say, okay, great, 73% accuracy. That might be really, really good if our task is difficult, right? If we're trying to predict whether a stock's going to go up or down, if you can get 73% accuracy, you're doing awesome and you can make a lot of money. If you're trying to predict whether or not an email is spam or not, 73% is not very good, and nobody's going to be happy with your email client because their inbox is going to fill up with spam. So the first thing that we're going to do when we try and sort of figure out how good our model is try and figure out what our baseline evaluation should be. So again, this is going to take a little bit of design based on what you're working on. So when we say baseline, what we mean is if you just do sort of the obvious stupid thing, you don't use any kind of fancy machine learning, you don't build in any sort of estimation of parameters, if you just do something that any intelligent system is going to be able to beat, then when we check against that, we have some idea if we're actually learning anything useful. So particularly in this binary classification task, the easiest baseline is called the majority class, right? So if the most obvious thing to do is if you're given a pile of movies and you're asked whether or not they're going to be profitable, you can just ask, well, are movies usually profitable? And if they are, you just say yes every time. And if they're not, you just say no every time. And you'll get something that's better than random chance. So let's take a look at what it is in this particular case. So here, It looks like we can count the majority class by taking a look at what the mode of our target labels are. And then if we just always predict this majority class, our accuracy score comes out to 78%. So this is saying if you just always predict the most obvious majority class, 78% of the time movies just are profitable. So if you say yes always, you're going to do better than whatever this is we learned up here. So this should send up some red flags for anybody who's working on a machine learning problem, right? If you can't beat the majority baseline, then something's kind of amiss, right? Because if your logistic regression just set the weight to 0 for all of your features and only use the bias term, so this is basically any machine learning model you're going to have has some sort of intercept that lets you capture the majority class. So if it set the weight to 0 for all of your classes and just use that intercept, it would score 78% accuracy. So we've done worse than the baseline. So this suggests some things that we might want to look into for debugging our model. Specifically, it suggests that we're probably fitting a little too closely to our training set, right? If we're looking at all of these examples and we say, okay, any movie that has action and adventure and romance and the keyword champion, then that movie is going to be profitable. It seems pretty clear if you think about it a little bit that like sort of this level of detail about every movie, if you string together like all of the keywords and all of the genres, there aren't that many movies that fit that description. So models are capable of just memorizing big training sets like this. So last time we talked a little bit about how to detect overfitting and how to regularize your parameters. And this week, we're just going to sort of leave that behind and forge on ahead with, okay, well, we've learned a classifier that does worse than the easiest baseline we can think of. But accuracy is just one metric, and is there something else we might be interested in measuring? So 3 terms that you might commonly see are precision, recall, and F-score, so typically an F1. So just can I get a quick show of hands? Has anybody, or for who are these new terms? Are these new to anybody, or should I? Cool. Yeah. So accuracy is a great measure, but it's got some problems, right? So if there's a big imbalance in your classes, then accuracy has the potential to do really, really well. So if you have a system that's designed to detect whether or not people have cancer, let's say, and you run it on the random population, if you just always guess no, that's a super strong baseline, right? Not that many people actually have cancer. So if you say no all of the time and just look at accuracy, your model is going to get like 99.9% accuracy. And if you don't think too carefully, you can just look at an output like that and say, I mean, that looks great, right? It's hard to beat 99.9%. But it might not be measuring exactly what we're trying to measure. So 2 of the big metrics that people like to use when you're sort of talking about, how does your system interact with what you're trying to learn? So if we're trying to find cancer patients, then what we might really care about is how good is our system at like pulling out cancer patients. So if you have a system that's really good at identifying all of the actual cancer patients, but also has a bunch of false positives. So basically, if you have a system that's paranoid here and overpredicts the true class we're looking for, then we measure that. That's the recall of a system. So a system that is very good at finding all of the true positives, but might also have a bunch of false positives in there, that's going to be your high recall system. Something else that people might care about is a high precision system. So here precision says, okay, like whenever you assert that something's the thing we care about, whenever you say, okay, this is a cancer patient, or whenever you say like this is a movie that's going to fail, we want to make sure that our classifier is really, really good at making that decision. And it's never going to send up false alarms, right? And so depending on what your application is, you might prefer one to the other of these. So for example, if you're Google and people are typing things into your search bar and you're giving them the top 10 results on the first page. What you really care about is making sure that those top 10 results are all relevant. So as this information retrieval perspective, you really want to make sure that like those top 10 things are precise, that you don't get any false positives in there. And if you happen, maybe there's some things on the internet that your search engine doesn't find, that's not a problem. There's plenty of information out there. We've probably given the user something they're interested in. Other things, so if you want a high recall system, let's say you're doing like drug discovery and you want to look up all the trials about the sorts of things you've studied so far. So if you're interested in solving like a particular disease with a particular outcome and you want to review the existing literature, it's really important that when you do your search, you get all of the documents, and then maybe you can throw the stuff out that's not exactly relevant to you. So given our kind of crappy classifier, let's see if the precision, recall, and F-score. So here F-score is a sort of an average of precision and recall that sort of balances the two. So let's take a look at what we get for our true and false classes. And we see that our classifier is really good at handling the true class, which is not surprising. If you just guess true most of the time, you're going to do pretty good. And it's really bad on the false class. Again, when we learn these parameters, the model doesn't care about getting these right that often, right? If you mess up on the false class, it's pretty rare. You don't get penalized that heavily for it. So we see we get only 16% of the movies that fail get tagged as false here. And of the movies that we tag as false, only 30% of them are actually going to fail. So if we think a little bit about these two metrics, we kind of realize that there's a way to trade off between the two of them. So, because any classifier, so here we've got our binary classifier, and when it makes a prediction about what class your item is going to be, it's generating probabilities, right? It's generating a probability distribution over the target labels. So any model that predicts what class of something is going to be says, okay, for this first thing, I think there's a 7% chance that it's actually false, and there's a 93% chance that it's actually true. And sort of what a classifier does implicitly is says, okay, whatever's got the highest probability, that's probably what it is. Does this make sense to everybody so far? Does anybody have any questions about why we might care about precision or recall, or what exactly they measure? Can you maybe sort of expand a little bit on what you mean by reliable?
I mean, which one should we consider that if it has a better score, our model will?
Right, yeah. Right. So if you're just trying to make one number go up, what number should you pick to like try and maximize? So in general, it's going to depend on what your application is. In practice, people like to just look at this F1 score, which kind of averages the two. And if you don't have any sort of other information about like what your client wants or what you're trying to target, if you make the F1 score go up, you've probably got a better model. So if we have probability distributions over the target labels, then we don't always have to just take the most probable class and say that that's the class we're predicting. We can either be really pessimistic or really optimistic. So if we're really pessimistic and we think that movies are wildly overrated and maybe people are going to stop going to movies as much, or it's just not going to be as profitable in the future, then maybe if something is if our model thinks it's only a 35% probability that something's going to be false, we might go ahead and say, okay, well, the model thinks 35%, but I'm going to go ahead and push that a little bit towards pessimism. I'm going to say anything 35% or higher probability of being false, like that's the new baseline for what it takes to be false. So anytime you have like a big class imbalance in your training data like this is a way of sort of correcting for that and pushing your model towards over-predicting a particular class. Or we could say that, we could push it the other way. We say if we really only want to predict false, if we only want to say a movie is going to fail when we're really, really certain it's going to fail, then we might require that the probability of a movie being false according to our model is really, really high, is like 0.8 or 0.9. So we'd say only if we're 90% certain this movie is going to fail, then we'll like set up a warning flag. So sort of touching on your question of how do you, if you're trying to predict, if you're trying to sort of tune this threshold, right? So if we move this threshold higher and higher, then we're making it so when our model says, okay, something's false, it has to be really, really sure it's false. That's going to make our predictions for the false class much more precise, right? Every time we say false, we're going to be certain that we mean it. But there are more things that could be false that we're not really sure about, and we're going to say, okay, maybe that's true. So even though our precision is going up, our recall is going to go down. And the converse is true as well. So if we say, okay, you know, if something is, maybe there's a slight chance that it's going to be, that it's not going to make money, we'll go ahead and flag that. Then we're going to, all of a sudden, we're going to start identifying a ton more movies that might not make money. Our recall is going to go way up, but we're going to get a bunch of extra stuff in there that actually ends up being profitable. So our precision is going to go down. So anytime you have a classifier, you have the ability to sort of trade off between these things. So here, if we take this pessimistic version, then we say that, okay, only classify something as false if there's a, or sorry, the pessimistic version, which says classify something as false if there's at least a 10% chance it's going to fail. So this says, you know, if there's any chance we think it's going to fail, classify it as false, and we run this as our threshold instead of just 50%. We see that our performance on the false class has gone way up. Our recall has gone from 16% to 86%. So we've gotten a huge gain in recall because all of a sudden we've identified everything that might be kind of marginal, but we'll take a hit in precision. But here our hit in precision, we've only gone from 29% down to 24%. So by moving the threshold, we've gotten an enormous gain in the recall for only a small hit to precision. So anytime you're tuning a model, if you think carefully about exactly what you're trying to measure and what your evaluation should be, you have the ability to move this threshold to target exactly what it is you care about. So something that is easy to do when you're trying to set this threshold for how to tune precision versus recall is you can pick a bunch of different thresholds, right? So if you can say for every threshold from 10%, 15%, 20%, 25%, you can step through all the thresholds and measure what your precision and recall are at that threshold and then plot them against each other. So this is your precision recall curve. And this is a very common way to figure out how to set a threshold and look at what your trade-offs are. So here we can see that as our precision goes up here, so we're moving further out on the x-axis, our recall goes down. But our recall goes down much faster than our precision goes up. So if we just ask our original model to optimize for accuracy or optimize for loss or whatever the built-in default optimization is, it's given us a point on this curve right about here, which was to say, okay, our precision was 28%, but our recall was only 17%. So here this is precision 0.28, recall 0.16. But our actual model can actually be any point on this line. And so by moving the threshold, we can say, okay, we'd rather have lower precision but higher recall. Any questions about what a precision recall curve means? Okay, so moving on from here, I'm going to talk about a little bit about the visualization tools that are available. So when people are sort of looking at statistics for their data set or trying to understand what values their data takes, or what things are related to each other and how they're related, it's very easy to just look at things like Pearson or Spearman correlation, or to look at means and standard deviations of your different distributions. And sort of printing out statistics and looking at tables is a great way to get started, but nothing tells you how your data is distributed quite like actually looking at it. And there's great plotting software. So here we're going to look at Matplotlib and Seaborn. These have been developed for many, many years, and they do almost everything that you really want to do right off the bat. So first we're going to look at some ways to plot your different variables. So again, there are a few different types of variables. There's numerical, right, is the most straightforward. This is just a column that takes on a bunch of sort of floating point or integer values. And so if you want to look at a distribution like this, I'm sure everybody's seen your humble histogram before. So here we're looking at how the budget variable is distributed, and we see that it's not normally distributed. There's a big left skew, and then sort of more and more expensive movies are less and less common. You see like a big bump. A bunch of movies tend to budget. This is 150 million. A bunch of them budget 200 million. And a bunch of them budget 250 million. So this suggests that maybe there's some kind of weird artifact in the data where people like to round to the nearest 500 million. But in general, lower budget movies are much more common. So this can inform lots of things, like do you have weird outliers? If you sort of rescale by the standard deviation, are you likely to produce sensible things? If your data is normally distributed, then you might make different decisions about like what your support vector machine's kernel looks like or things like that. So the next type of interaction we're interested might be the relation between two numerical variables. So each of our movies has some amount of runtime and some amount of budget. And the first thing that somebody might want to do to look if there's an interaction between the two is either compute the correlation coefficient, which will give you some number, or if they want to understand more deeply what the interaction between the two of them looks like, you can make a scatter plot of the two. This scatter plot has sort of one big issue with it. Does anybody want to tell me what that is? Looking at this, can you sort of really tell what's going on for most of the stuff here? Right? This turns into a big blue blob, right? There's huge occlusion, our points all overlap each other, and there's kind of no way to tell exactly like, okay, are there more movies at a runtime of 100 minutes or at 120 minutes? So this is very, very common to have these big occlusion issues if you have lots of points. So here are a couple tools for how to deal with this if you want to look at scatter plots that are very, very dense. You can do a little bit by sort of making the plot bigger, making your points smaller, making them so they're just outlines instead of filled in, or adding some sort of transparency. But these are all just sort of putting off the inevitable. So for any sufficient amount of data, your plot will get too crowded. So these are using the standard matplotlib functions for histograms and scatter plots. But the more advanced plotting library is Seaborn, which we import as SNS. And this is built sort of as an extension to matplotlib to do anything extra that you might want to do. And it's designed to take in pandas data frames, which is super convenient because that's what we've been doing all of our data manipulations with. So here it's going this joint plot is going to take a data frame, which is here's our trained data, and we're going to tell it which column we want as our x, as the runtime, and which column we want as the y, which is our budget. And so this will give us the same scatter plot, but in addition, it'll plot the marginal histograms on each of the axes. So here we can see that, and this is the distribution we saw before of budget with a big sort of tail down towards 0. And we can see that runtimes are a little more normally distributed. They're skewed towards slightly longer movies, but you get this nice sort of sloping tail in the distribution over here. So again, this kind of only partly solves our issue. We still have lots of occlusion here. We can get an estimate of what the distributions are, but it's hard to actually make use of this part of the plot. So Seaborn again provides an extra tool for dealing with this, which is the kind of joint plot we want. And here we can ask for a hex plot, which gives us the density of the points. So here it makes a little hexagon for each square and just colors it darker if there's more stuff in the square. So now, not only do we get a nice view of the distribution of our different numerical variables, but we also get a really clear look at the densities. And so we can see here the movies with low budgets tend to really only be about an hour and a half, maybe a little bit more, and they start tailing off. So you get fewer and fewer longer movies at low budgets. So this is a pretty useful way to look at the way two numerical variables interact with each other. Numerical variables are only part of the things you have to deal with. We also might be interested in categorical variables. So I'm going to give you kind of the Rolls Royce of the categorical versus numerical data plot here, which is the violin plot. Okay, so let's, so here we're going to, in general, whenever you're plotting a categorical variable, you're going to have sort of a different plot for each different category, right? So this is the principle of small multiples, where if you want to compare across different categories, the easiest thing to do is create a little visualization for each of the discrete things you're interested in, and then line them all up next to each other so you can make easy visual comparisons. So here, what we're going to plot is each different genre of the movie versus the budget. So here we're going to look at it if there's any sort of interaction between category and budget. And what a violin plot is, if people are familiar with box and whisker plots, so this is something where you plot the mean right in the middle, and then you plot extra information about the distribution sort of along a vertical axis. In a box and whisker plot, you plot something like the quartiles. So you say, okay, 50% of the data is within this box, and 100% of the data is within the whiskers. Here, we can go ahead and plot the full distribution of the data. So this is basically a little histogram on each little slice of the y-axis here. So we see that documentaries tend to be very low budget, right? This thing bulges out towards the bottom of the budget. And things like horror or music or drama or comedy tend to also be towards the lower budget, but do have a few more examples up here that take on high budget. Or something like animation or adventure or fantasy are the really, really high budget categories. There isn't that much weight down in this low budget part of the plot, and you see them sort of at all these different ranges of high budgets. So these are sort of the examples of how you might plot the interaction between your variables. I've sort of been alluding to wanting to quantify the relation between them this whole time. And the easiest way to compute the relation between your variables, if you have different numerical variables, you just calculate the correlation. There are a number of different correlation coefficients that people are interested in. But we can just take standard correlation, and here we can look at sort of the correlation between our budget, runtime, revenue, popularity, vote average, and vote count, and just see if there's any strong links between these different categories. And we can plot the links in a heat map. So all of these values, we see the correlation. Correlation is going to take a value between 0 and 1 here. And we're going to color the square darker if there's high correlation and lighter if there's low correlation. So we see there's very high correlation between vote count and revenue and vote count and popularity. We see there's high correlation between revenue and budget, but sort of lower correlation between the average score, the vote average, and things like revenue and popularity, which is kind of interesting and might inform some modeling decisions. So these are the basic visualization tools that should get you through almost anything you need to plot. Sort of, and some composition of these in small multiples should get you sort of an intuitive look at what your different variables are representing. So I'm just going to recap really quick the things we've talked about across all 4 weeks. And then I'm going to open the floor up for any questions if there are sort of details that people feel like they would like a little bit more information on, or things that weren't clear, or if people want suggestions about things to think about in the future. So first, we went through what it takes to set up a task. So when you're sort of diving into a new task, it's important to figure out exactly what it is you're trying to learn. So your model is going to need to make a prediction, right? It's very easy to sort of say, okay, here's a column in the data set that I want, I'm going to learn to predict this column. But if you stop and think a little bit, maybe it's not always the case that that column encodes exactly what it is you're trying to learn. Because every machine learning model is a means to an end, right? It's trying to be part of sort of a useful application somewhere. And that useful application might not be predicting exactly what the column is. So think a little bit, maybe you can derive a more useful value from one of the columns, or maybe you can collect a little bit of supplementary data to sort of figure out exactly what it is you're trying to achieve. The next thing to think about when you're setting up your task is what data will you, so in your actual application of your model, what kind of data are you not going to have access to? So in this movie data set, there's lots of really rich information, like the vote count or the popularity or things like this that tell us a lot about whether or not a movie is going to be profitable. But if our goal is to produce a system that will predict if a movie is going to succeed or not before that movie is released, then we won't have access to any of this information. So building a model that takes in revenue and popularity and vote count and vote average and predicts whether or not it's going to succeed we might be really, really good at this and get something that has a sort of amazing performance, but there's nowhere that we can actually deploy such a model because we're not going to have a realistic setting where we have access to all of this rich information. So after you sort of figured out what it is you're trying to predict, what information you should use, then we go ahead and think about how do we encode this. So this is how do we do our numerical and categorical transformations, and how do we sort of normalize everything. Then once we've got all of our data set up, we have our nice matrices generated, then we're going to think about sort of how do we select and actually train our model. So the first sort of divergence here is, are you trying to do some sort of numerical prediction? Do you want a regression? Or are you trying to do a classification problem and predict one of your categorical variables? Then how much data you have should inform what class of model you're looking at. Some models work very well with low amounts of data. So this is anything that doesn't require sort of big averages over sort of the global state of the data. So something like k nearest neighbors, where it just looks at sort of the surrounding points and uses similarities between them to predict whether or not something's going to be similar. That's not going to be that sensitive to how much training data you have. Something like a decision tree, where you look at all the different values and sort of say, okay, you know, if the budget was higher than 50K and the runtime was less than 100K, then look at like horror movies and make a decision based on that. Something like that depends a little bit on sort of like the individual components and maybe doesn't require quite as much data to train. Whereas models that have lots and lots of parameters tend to require lots and lots of data to fit. So, for example, neural networks are a great example of something that has tons of parameters in it, because the more parameters there are, the more freedom you have to sort of pick out sort of specific predictions. If you have lots and lots of parameters and not that much data, it's very easy to set all of your parameters just so that you get great performance on what you're trying to learn. Which in this case is you get great performance on your training data, which isn't particularly useful down the line. And then finally, these are just sort of some rules of thumb to guide how you might think about these things. There's no substitute for actually trying a bunch of different things. So especially with tools like sklearn, where you can just pull different models off the shelf. So here you can just say, okay, train a logistic regression, train a linear regression, train a naive Bayes classifier. There's no excuse for not just trying a bunch of stuff and seeing what works best. And then as you do more and more of this, you get a better intuition about what sorts of things will work for different sorts of problems. Again, while you're doing this, make sure that you're using your development set to make decisions about how you're going to model things. And then finally, once you've settled on a model and an approach for encoding your data, make sure you think carefully about how you're measuring your results. It's very easy to measure things like accuracy that aren't exactly what you're trying to learn. So it's very important to sit down, maybe talk with whatever system you're trying to deploy to, figure out what exactly your application is, and do things like figure out if you're trying to maximize precision or recall, or how you're supposed to balance the two. And then finally, make sure you're using visualizations as you go. Like, nothing is going to be a good substitute for just plotting distributions of your different data. This lets you identify outliers, lets you sort of discern trends in your data. If there's strong relations, that might inform sort of different types of features you might want to engineer. Just looking at summary statistics is never going to give you the whole picture of what your data can tell you. And those are the basics of off-the-shelf machine learning. And if anybody's got any questions, I'm happy to stick around and answer them.